Hi, and it's another dose of Channel Engineer. Okay, so today we're going to be covering something which you don't learn in schools, universities and what have you, or at colleges when you study electronic engineering. Okay, now when you do your, I don't know if you can hear that, some drilling going on in the background, unfortunately. Hope it's not going to affect this too much. But yeah, the heating engineers seem to be constantly drilling. They've been doing it for the past hour now, non-stop. It's been a right pain. It's giving me a headache anyway. Yeah, we're going to be covering something that isn't really covered, because it opens a whole can of worms. Okay, and it really does give your lecturers and teachers a complete headache, and they like to avoid it as much as possible. Okay, and they leave it up to technicians, things like me, people like me, to deal with when you do your lab sessions. Okay, unfortunately, we can't really spend much time doing that. Okay, because you're doing what? You're doing your experiments. Your lecturers want you to do your experiments. Teachers want you to do experiments. They don't want us to. We don't really get that much time to spend on this anyway. Yeah, so what's it going to be? It's going to be all about components, okay? Specifically component selection, picking out the right ones for the right jobs and making the right decision when you come to, you know, saying what component you actually want to use. Now then, when you do your lectures or your circuits and what have you, you're generally, if we take the resistor for an example, okay, you're generally taught that that is the symbol for a resistor, or that is the symbol of resistor. Okay, it's either that or that. Depends on what part of the world that you're in, depends on where your teacher's from. Okay, it'll either be one of them two. Okay, and you'll also be taught that a resistor resists. Yeah, right. Okay, we all know that. And it's got a symbol R. Okay, then you want to call it R1, R2, R3, R4, you know, dot, whatever. And it will probably have a resistance of, say, 10 ohms. Yep, okay, no biggie. Yep, that's right. Perfectly fine, okay. They might even touch on tolerance, okay, of resistors. Okay, plus or minus its value, okay. They'll only generally touch on that, okay. They won't tell you why, but it will have it. Okay, and that's as much as they go on, and then they start building and constructing circuits in, I don't know, parallel, series, you know, meshes and what have you, and they get you working it all out and say, yeah, okay, so you work it out, brilliant, okay, this calculation was all crap, okay, and after a time you get so ingrained into this that a resistor is just this symbol, okay? When you come to doing your project, okay, or you start building things, okay, you hit a brick wall, because there's more than one type of resistor out there, okay? And it's something that you're never actually taught, okay? For example, if you go into an electronics lab or anything, in schools and universities and stuff like that, you'll generally encounter resistors, things like that. In your lectures you encounter resistors, and they're generally things that look like this, okay, you see that, okay, that is a resistor, okay, and you'll get into the habit of thinking that that is a resistor. But when you come to search online for a resistor, a particular value, a 10 ohm resistor, okay, that they told you to use, or you calculate it out, you hit a brick wall because of this. Okay, what do I have? I have tons and tons and tons of resistors, okay? These are all resistors, different types of resistors, okay? And it's not just resistors, it's every single component imaginable. Capacitors, diodes, inductors, chokes, coils, digital electronics, you know, you've got your gates, you've got your microcontrollers, you've got your whatever, you've got your amplifiers, your the list is endless, okay? And if you imagine that, you know, that symbol for a single resistor is actually it could denote actually any one of these. So that's what we're going to be doing today. Okay, which one of these resistors do we pick now on that sheet? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, you know, there's almost 20 resistors on there. Okay, they're all different types. You got carbon film, metal film, carbon composition. You got wire wound. You got different combinations of, you know, the actual shapes. You got wire wound in, you know, heat sinked wire wounds. You got wire wounds in ceramics or ceramic wire wounds. They used to be called, now called ceramic wire wound. You got wire wound on silicon. You got metal oxide. You got, you know, your box standard wire wounds. Okay. On the ceramic, you got different ways of mounting styles. So you got solder tags, wires, axial, radial. Okay, both the same, but different connectivity wise. And you got surface melt down here. You might as well do little blips and what have you. So it's really, really important to pick out the right one for the right job. That's why there's so many different ones. Okay, now all of these could all be 10 ohms. Okay, but you're not actually taught that. Okay, you just taught that one symbol, that's a resistor. Okay, and it looks something like this, and yeah, that's it, until you come to doing your own projects. So how do you choose which one you need? Let's go through it. And that all boils down to the scenario that you're in. Okay, first of all. So, from the top, you gotta make a choice. Okay, first off, choice. And you have to assess the scenario, what you're in. Okay, now the scenario can either be one or two things. Okay, it's either going to be a design, or it's going to be something like a repair or a modification. Okay, so design on paper, or something you know, built. That you have to deal with, something physical. Okay, you might have a power supply that you have to change a component in or modify. Design, you might be actually designing one. Okay, you've got two different scenarios to consider. Now we'll do the design one first. Okay, and design, okay, choosing the right resistor. Now, like I said, it could be the same for any component, okay, but the principle is the same thing, so we'll just cover the resistor for that for this time. Okay, so you've got your design. It could be a potential divider, okay, and you designed it to be, say, a 1K and a 10 ohm, okay, 1K and a 10 ohm. Which one do you need? Well, you have to do some extra calculations. Okay, what are the properties of your resistors? Well, it's obviously you've got your resistance. Okay, you've got your tolerance. Okay, so you've got your resistance in ohms, you've got your tolerance usually as a percentage, you've got your temperature coefficient in degrees, which I never tell you about, and you've got you've got power. How many watts can your resistor dissipate? Okay, you've got current flowing through it, you develop a voltage across it, it's going to start radiating, you're going to start dropping power. Okay, it's going to start heating up. Yeah, power. You've also got, stability. which you're never told. So you're not really told about temperature coefficients. You might touch on power, okay, you may do Ohm's law, you may do power, you start working out, right, well, what's the power across this resistor, okay? Yeah, it's all very well and good, but they don't actually tell you that a resistor can only take so much power. That's why you've got so many different types. So you've got high power, and you've got, you know, low power ones, okay? The actual power is, you know, if it's 10 watts and it's a 10 ohm resistor, then you're stuck with picking a particular type of value that is, you know, that can handle that, and you may push it down a different route. But also you've got stability, which could be, you know, stray capacitance, or it could be stray inductance in there. Okay, so you have to imagine, wire wound, it's a coil, okay? Coils have inductance, okay? You will get some inductance, okay? Same with these, okay? You've got a lead on here, you've got wire, okay? The wire on its own will have an inductance, it'll have a stray inductance. For general purpose circuitry, it may not be a problem. For RF design, okay, or radio design and things like that, it all adds up. Can be a problem. Things like capacitance, if it's wire wound, you're going to have some stray capacitance between the windings. Okay, so it's going to shift your RF signal, so it's quite important. Okay, so stability wise, you know, how accurate is it? Okay, how close to 10 kiloohms is a 10 kiloohm resistor at 1k? How close is a 10 kiloohms resistor to 10 kiloohms at 1 gigahertz? Okay, at 1 gigahertz, probably nowhere near it. Okay, unless you start using things like surface mount components, high stability surface mount. That's all this sort of stuff that you have to pay attention to. Okay, and these properties all boil down partly to either your design calculations, calcs. Okay, so if you've got your 5 volts going in, okay, how much current flows through, you can work out the power. Okay, power dissipation. You can say, right, well, I'm dividing my voltage down, okay, if it's a 1% resistor tolerance, this is how much the ratio is going to vary slightly. So, or if it's a 5% of that, but it's up to you how much you can hit and miss, you know, how close you want your results. So, calculations, you have to calculate, you know, the output for tolerance, you know, if my resistor is 5% greater than what it should be, work it out. If it is 5% less than what it should be, work it out. Okay, what sort of ballpark figure are you actually going to design for? Same with power. Find out how much power is being dropped across your resistors. Okay, very important. If you pick out a resistor, or you buy a resistor which has got a lower power rating than what's actually going to be developed across it, okay, and what it's actually going to, you know, drop, then you know, you could end up setting fire to your resistors. You know, burn out your circuits. You can just switch it on. You're just wasting some money. Okay, so for calculation wise, you can work out your power. Okay, your tolerance, your power in watts. Okay, your resistance. Okay, they're the main things. The other things, the stability, temperature coefficients. Okay. Dimensions, sizes, okay, how big you can get away with it, is all down to your design constraints. Okay, do you have any design constraints? What sort of environment is it going to be? Is it going to be in a hot environment? Is it going to be in a humid environment? Is it going to be in a particularly cold environment? Is it going to be at room temperature? Okay, is it going to be particularly hot because your components are mounted near regulators or heat sinks, things like that, you know, and power supplies? Is it going to be a problem? So design constraints dictate what temperature coefficient that you're going to have. Okay, it also dictates the stability. You're going to have things like that, and the size. Okay, size. Are you working? Does your circuit have to fit into a very small place? Okay, is it quite confined? You have to aim for small components. Small sizes means low wattage generally. So you may have to go back to your drawing board and redesign your values so that you have a lower wattage dropped across your resistors. So instead of a 10k, you might have to change this to a 10 and 100. Keep your ratio, you keep your voltages, and what have you. Current goes down, so therefore the power dissipation is a lot lower. So you can fiddle about with size, okay, by going back to the original. Stability is all about, you know, what kind of situation, you know, what signals are passing through your resistors. You know, is it AC, is it DC? You know, do you have lots of transient signal, things like that? Will a, you know, will a picofarad, you know, stray capacitance affect your circuit? You know, will a microhenry of inductance, or points of a microhenry inductance, depending on which that you want, affect your signal? Is it a filter? Okay, is it a tank circuit? Is it a filter circuit? Oh no. Is it for a pump charge or anything like that? Are these other things going to affect it? And that all goes into your design. Okay, it's all part of your design constraints. Okay, and that's how you pick out which one you actually need. So, for example, I need a resistor. I've calculated it out. I need a 1 kilo ohm, half a watt, you know, 5% tolerance. Okay, temperature coefficient doesn't have to be important because it's going to be at room temperature. Size is going to be pretty small. Okay, it has to fit inside a very small case because I'm modifying a design that's already been done. I've already got already boxed up. Okay, and I want to modify it, so it might have to fit into a small case. The size is going to be an issue. Yeah, okay. Stability wise, it doesn't really matter either. Okay, because it's a DC circuit, I'm not passing any ACs through it or anything like that. Okay, it's just a box standard divider. Okay, and that's the resistor that I want. So which one do I pick out? Well, it's not going to be the huge chunky ones because I'm short on the size. Okay, so it's going to be quite small. So I might want to go to, you know, extremely small resistors. Trouble is, these are only coming in at about points of a watt, right? 0.1 watt power rating. So that's out. You move on, okay, you say, right, next size up, carbon film, okay, perfectly fine. Trouble is, I don't know, 0.33 watts, still too low. And you slowly move on, okay. This particular one, okay, another carbon film. 2 watts, yeah, it will do the job, but, you know, it's slightly too big. What the hell do I do? Okay, right, well, I'm going to go to the wire wounds, okay. I can get my silicon wire wound ones. Well, these only come in at very low ohm resistances, so it's all about picking and choosing, finding out the right properties that match that particular type of resistor, and that points you down the line. Now, if you know all these design characteristics, if you look for your components on places like Farnell or RS and things like that, you can actually do parametric searches based on characteristics, and if you've calculated everything out correctly, you can actually plug in all these values, your tolerance, your resistance, your wattage, your temperature coefficients, things like that. Okay, you can even do size and dimensions, and it will slowly filter down all of your components that you can buy from them that fits your particular criteria, and that's how you choose. Okay, but in order to find out what components are, okay, if you're just beginning into this, you've never seen components, okay, you only ever seen resistors like the carbon film ones or the blue metal film resistors, okay, you may not have encountered these, okay. So if you've been, you know, messing about on whiteboards, on paper, designing your circuits, you've never actually looked at components, it's time to stick your head out from above the clouds, okay, grab a catalogue, take a look at what's out there, okay, find out what resistors there are, okay, find out the differences. So like I said, your teachers and your lecturers won't tell you this stuff because they'll have to do a potential divider sort of circuit and go into all detail about all these other values, okay, every single bloody circuit that you do, okay. And it's not just resistors, it's capacitors as well. Capacitors might have a power rating, but they've got voltage ratings, okay. But if you're in your lectures, you'll only see a capacitor which will look something like this, okay, a capacitor. Well, you get polarised capacitors, okay, your electrolytics, your tantalums and stuff like that. You get non-polarised things like ceramics, polyesters, micas, polystyrene. There's tons out there, all different sizes, all different pitches, all different voltage ratings, all different capacitances, all different types of materials, all used in all different kinds of situations. And you'll only work out which one you actually need by going out there, taking a look to see what is available, and also working out all the other calculations involved. Okay, it's all about picking and choosing, and sometimes in your design constraints, because you're so constrained, or your design is so open, you've got a huge choice or a very, very small choice. Okay, and sometimes you do have to make compromises. Okay, sometimes you might have to use a resistor with a super huge wattage, but it's really, really cheap. Okay, compared to a component which has got a very small wattage, which is really, really expensive because it's been more highly engineered. Okay, it might be a it might be a current sense resistor, very, very, very small resistance. Okay, but it has to withstand high wattages. Okay, depending on what situation that you're in. So you might have to go for the huge chunky one, but your design constraint says that you can't go for a huge chunky one, so you might have to dump the metal one and then try and go for the ceramic or the ceramics type resistors. Okay, you may have to be very, very on the edge of your power rating, and you won't be able to overrate it, or you might be able to overrate it whacking one of these, and your design lasts a hell of a lot longer than it would do with one of these. It's all down to that design. Okay, so that's your design side of things. The other way you pick components, okay, is the physical method. You have a circuit already in front of you. Okay, like let's see if I can dig out one. Right, back. You might recognise these computer motherboards. Okay. This is one that I've been salvaging components off. Okay, a couple of these sockets, so slowly stripping them off. Okay, really useful. Okay, you might think of all crap electronics, you know, circuit boards and whatever, chuck them in the bin, get rid of them, what have you. But you know, don't be afraid to salvage parts. Okay, do for your own projects and what have you. It's a brilliant source. Okay, old boards like these, people are chucking them out. Hey, you can take the chokes off them, you can take the sockets off them, you've got heat sinks on them, you've got, you know, all kinds of things. You've got buzzers on there, you've got LEDs on there, edge connectors. It's free, go reading. Okay, you don't have to buy a lot of electronics if you're just starting out, you can just strip stuff apart. Anyway, like I was saying, you've got the physical. Okay, now if you was to replace, say, one of these capacitors is blown, okay, it's gone bulbous, okay, you have to replace it. How would you know what one to replace? How do you know what component it is? Well, first of all, the only way you can do it is, like I said, stick your head out from the clouds, get used to what components look like, okay? They can vary a great deal, as with the resistors, okay? Actually, yes, we'll go back a stage to this sheet down here. Okay, you can see all my resistors here. Yeah, here's a good test. Okay, one of these isn't, in actual fact, a resistor. And this is a little game that I've started playing with the students that I look after in the lab. Okay, and a lot of the time they pull out this. They say that's not a resistor, that's a semiconductor. Okay, it's a diode, or you know, something like that. That's not a resistor, that's the one. And in actual fact, okay, it's I'll tell you at the end. Okay, see if you can guess what one it is. Okay, because this is very important. Okay, some components can look like other components. Okay, resistors can look like capacitors. Okay, some capacitors can look like resistors. The axial ones can. Okay, because they just look like a very small bead. I've had a student in the past where I've got this one from actually. that he mistakenly thought it was a resistor. It isn't a resistor. Okay, and he worked out all his, done all his circuitry and everything, built his circuit, soldered it all up, he plugged this one in. Okay, he got it out of a, you know, he salvaged the component for himself, and yeah, he turned around and said, it's like, oh, the circuit's working. And so I took a look through it and I almost missed it. And I spotted, oh, hold on a minute, that isn't what you think it is. Okay, so, you know, get used to what components look like. Anyway, getting down to these, okay, capacitors here, how do you know which one to pick out? Okay, if you've got to replace it. Well, on caps and on resistors, you've got either your colour coding or your values written directly on. On caps, it will have the values. So on these ones around here, okay, these are 1,500 microfarad resistors are written on, and they've got a voltage rating of 6.3 volts. Perfectly fine. That's what you can go off and go searching for. But you'll get them in all different sizes, okay, and all different types. Now these are electrolytics, okay, and you generally only ever get that value in electrolytics. Okay, you'll probably find some super caps about that size as well, but they're electrolytics, and the only way to pick it out is by doing your working through, similar to what you did with your designing, except you're working backwards in this case. You know what the value is, okay, and you know what the dimensions are, so you measure the dimensions, you know all that, you can go off and buy the right one, okay. If you look through a catalogue, you can flick through the pages quickly and you can actually see and identify the actual component itself, what it physically looks like. So it's more observational rather than calculating. That is, if you're doing it in the real world, okay, you have to get really good at observing, okay. So it's not only the dimensions, okay, its length, its height, its width, it's also its pitch, okay. And when you go through, you probably find half a dozen all matching that, and you can narrow it down a little bit more for tolerance. You can mash it a little bit closer than what it could be. You may want to go over the voltage ratings slightly on your caps or on your resistors, provided that they fit the board. But you also have to be careful to pitch to make sure it actually fits the holes, and also your wire, your lead thickness, okay, also fits the holes. I mean, it's no good buying, you know, it's a 10 ohm resistor that's gone. You buy a 10 ohm wire well because it was dirt cheap, or you had it laying about, you know, your wire, you know, it's about 1 millimetre thick. It may not go through a hole because your hole's only 0.8 millimetres wide. So you have to be very, very good at making observations and deducing what one it is. If it's a blown component, okay, one that's burnt out, you have to make some other observations. Take a look at the components that surround the actual area of your board, okay. Find out what the most common one is, see if it matches up to the right footprint, you know, are there any markings on your board, okay. If it's a, I don't know, if it's a cap that's gone, okay, the top of your cap is probably blown off, okay, it just leaves a little plastic ring at the bottom with two little legs sticking through it, okay, so you got an idea of the width, okay, the diameter of your cap, okay. You'll know it's a cap probably because it's got markings on there. It'll have a plus sign on the board if it's actually a polarised capacitor, which more than likely will be. If it's you know, if it's blown off the board, it's probably electrolytic or something like that. It could even be a tantalum, okay, because they're just as bad for going and whatever. Or it could be, you know, if you've got two wires sticking out of the board, okay, your component's not there. It could have been a resistor that's burnt out, okay, it's just left you there with a piece of carbon mess or something like that. But you read the board and you probably have an R value of R1, R2, R3, so you know it's a resistor, and you can, you know, work through it. Gauge the size, the spacing will tell you roughly what your power should be, okay. If it's a particularly large area, you've got a wide area, it's quite wide or it's quite long, it's probably a power cap or something like that. If it's quite small, narrow, you know, low power, if the marking's all been burnt off, you can take a look around the board. You'll probably be in parallel or in series with other resistors, so you can get an idea of roughly what value it was, okay. Or you can go into take a look at a similar board and find out what it was A little bit more difficult if the values have, like I say, been you know, burnt off or distorted or overheated. They're unreadable. So you have to make some guesswork. With electrolytics, it's quite easy because you know, they are proportional to the size of what they are. So if it's quite a wide cap, it's going to be quite a high value of capacitance. You can try and mash it up with other ones that are on a board. If it's a board like this motherboard, then you generally, okay, those particular widths of capacitors or heights and whatever will be all the same value, okay, and the usual grouped around in the same areas. Like these ones are all 1500s. The ones that are in between here, these are all 1 micros. The ones over here, okay, you got some 470s and some 220s, okay, and they're all the same sort of dimensions, all the same sort of size, so you can get an idea of what the values are by observing the components that are actually surrounding those ones that have gone. Okay, so that's how you do it in the real world, in the physical world. Okay, it's all down to observations and trying to hazard the best guess. Okay, it doesn't always work. Okay, it is difficult to do, but yeah, that's what it is. So for design wise, you're really stuck with design constraints and calculations. For the physical world, it's all about observational skills, okay, the physical characteristics, okay, about which one that you actually pick. And the only way you'll find out what component you need is by you know, looking about, see what's out there. So yeah, that's it for that one. And like I said, it's the same for all components: capacitors, inductors, resistors, and so on, diodes. Okay, get used to what they look like, get used to the types of packages, you know, and it should make your life easier when you come to actually buying components for your projects, okay, and determining what ones you actually want. Okay, because it's no good going out and buying 1,000,001 2-watt resistors, you know, at 10p each, when you could go out and buy 1,000,001 0.25s. Okay, at you know, a quarter of the price, things like that. Sometimes it does come down to cost. Hopefully that's been of some use, okay. And before I go, it was in actual fact this component right here, okay. This is the one, looks like a resistor, it's got colour bands on it, yep, it's red, brown, gold, okay, could be a 220 ohm resistor with a 5% tolerance, okay, very similar to, you know, the one below just there, or the one above it just there, you know, it looks similar, but in actual fact that component's an inductor. It's a 220 microhenry inductor. And like I said, the only way to do it is by taking a look out there, see what components there actually are, and paying attention and making really, really good observations. Because if you take a look, you can actually see the shape. Okay, it's triangular where the windings on the bobbin, okay, it's a ferrite bobbin, and the windings have actually started at one end and they're peeled off halfway and they're slowly tapered down. Okay, left with a bobbin shape with some wire wrapping around it, very similar to you know, that style. You can see that, okay, same sort of thing, but you have to be particularly observant. And the only way that you'll actually, first time round or first couple of times round, will notice that as an inductor, or have a suspicion that it's an inductor, not a resistor. So like I said, stick your head out from amongst the clouds, see what components are out there. Okay, and you will actually find those, okay. Inductors do share the same colour coding as resistors, except instead of everything being in ohms, okay, in microhenries. Capacitors are the same, you can get colour coded capacitors, okay. And yeah, and just for reference, okay, this one here, not a semiconductor, that's a thin film resistor. Thick film resistors, wire wounds, carbon films, yeah, blue metal film ones, you got light blue silicon wire wound ones, you got ceramic wire wound ones. These little ones here, we take a look at that, they're quite very, very tubular, okay. They're very, they look more like a little plastic rod with two wires coming out in. They're your carbon compositions, okay, instead of a film wrapping around a ceramic or something like that, or a metal film wrapping around ceramic, or carbon film wrapping around ceramic, whatever. Okay, it's actually a plastic outing with a mixed carbon composition in the middle, there for high stability. They're not really used so much nowadays because the stability of resistors has improved a great deal of time, okay, but you can still buy them, okay, they're still out there on the market. And not forget our little surface mount resistors, okay, radial ones, wires out the end, wires coming out both out of the end, or you got axial where they're coming out of either end. And so there's loads of different components out there, loads of different shapes, loads of different sizes, loads of different footprints, loads of different pitches, loads of different connectivity types. Okay, so you've got tabs, wire, SMD, so on. Capacitors, exactly the same thing, except you've also got screw terminals on capacitors as well, and so on, you know. So that's it. Yeah, have a look about, see what there is, okay, don't get caught up in the old idea that that is the symbol of resistor, and if we want to go out and buy a resistor it's going to be pretty straightforward, okay, that's the symbol of capacitor, you know, same ideas, that's a diode symbol, okay, a little triangle with a line. Well, you go out into the real world, that doesn't exist, okay, so get an idea of what's there, the different types, the sort of characteristics that they've got, the pros and cons, okay, because each one's going to have its own pro and con, that's why there's so many of them, okay, there's tons of them out there to fit your design, and it's up to you to pick the right one for the right design. So, that's it, see you later.